start off. The last thing we have used Gauss law to find the electric field to different distributions. That was the last thing that we did. Great. So today it will be a little more theoretical and the important part. So let's go ahead with this. And others, do keep your cams on. Field inside a conductor. So we want to study what happens if you keep a conductor in an external electric field. And this will form the basis for what we're going to discuss. So let's see. Consider a conductor is placed in an external electric field. Now you need to understand what is a conductor exactly. Basically, a conductor is a material which has a lot of free electrons. So if you take a conductor, it has a lot of free electrons. What are free electrons? These electrons can jump from one atom to another. They can't come out of the lattice, but they can move inside the lattice. And now if you try to apply a field, E bar, all these electrons will get attracted opposite to the field. Because electrons are negative charge, they move opposite to the field. In this process, what will happen? So these free electrons move opposite to the field and accumulate on the surface. I'll wait for a few more minutes, then I'll start removing you from the classroom. So no issue, you can keep your cams off. I'll just put you in a waiting room. You can wait. So now what would happen? Now, because of this side here becomes negative charged. This side starts becoming positive charge. Again, remember, positive is simply the absence of electrons. This external field is still there. But now what happens is induced charges. So these charges which are coming on the surface, I'll color them. These things will generate a counter field. So if you look at an electron in the middle, this electron is getting attracted by this force, which is E. And also these induced charges are pulling it to the right. This is an intermediate stage. So what happens? The induced charges so this minus on the surface and this plus on the surface, they will create a field in the opposite direction. So we get a field E induced in the opposite direction. So basically this field starts fighting with the external field, opposite to the external field. But initially, right, the external field is still stronger. Suddenly you won't become strong. It will take some time for the charges to accumulate. So the F external is still greater than F induced. So what will happen? The electrons will keep going. The electrons will keep accumulating, keep accumulating. At some point, you will reach a steady state. At this point, you have accumulated so many electrons, this thing becomes negative. This becomes positive, and they generate a counter field E Remember, the external field is still there. And these two become equal. So now if you look at an electron here, this electron is pulled by equal forces from both the sides. This will become F external. This becomes F induced. We always study the steady state. So after some time, this thing happens in some nanoseconds. F external becomes equal to F induced. This is not drift velocity. Drift velocity means they're continuously moving, right? This thing reaches steady state and they stop. That we will see in current. Therefore, net force is zero. Since the net force is zero, therefore net field is zero. Now look at the word net field is zero. Let me give you an analogy, okay? Think of like this. I'll get back to the previous page, but listen to this analogy. Let's say I have two rooms connected by a small passageway. I'm standing here. I'm a very strong person, let's say, right? And let's say there are 50 people here and there are 50 people here. They all are sitting comfortable. They're happy. Now, what I started doing, I'm standing here and whoever comes close to me, I'll catch them and I'll throw them into this room. That's my job. I'll take you and throw you into the other room. I don't know why. I'll do that. So initially, what will happen? I'll take some people as they're coming, I start throwing them. Let's say this becomes 45, this becomes 55. What do you think happen? There will be little resistance, right? Because this room is getting crowded and this guy does not want to go, but still I'm stronger. So I'll keep pushing you more and more and more. At some point, this will be 30, this will become 70. Now people will start resisting really badly, isn't it? When I catch someone and try to throw, that guy will completely resist, like, I don't want to go there. The people here who are already crowded, they will try to push him out, boss, don't come here. And here it is so empty and spacious, the guy does not want to go. But still I'm stronger. So I'll keep pushing it. Here it will become 20 and here it will become 80. At this point, the resistance is so high, even if I try to push, I can't push the person anymore, isn't it? We have reached a steady state. You're getting what we did? So here I am the external electric field and people here are the free electrons. Now imagine if I just get away from here, what do you think will happen? The moment I get away from here, the people here are all crowded, they'll start pushing back here and they will stabilize till it becomes again 50 and 50, isn't it? So the reason you're getting the charges on the surface is because of the external guy is making it unbalanced on both the sides, right? You have created a counter force. Now, if the external person is not there, will there be any counter force? There are 50 here, 50 here, everyone is happy, done. So the counter force comes because some guy from external is coming and pushing them, and you're creating induced charges. And these induced charges fight with the external field. Is this making sense? Something similar is happening here. Now, in case of current electricity, what happens? The same example which I gave, imagine there is a secret passageway from here to here. Now, what do you think will happen? Every time I struggle to push people here, they will find a secret way. They'll go back to this room again, isn't it? That's what we call as a current flow, and that's what a battery does. So in this case, right, you'll never reach a steady state. I'm pushing and they're coming back. I'm pushing, they're coming back. So the current keeps flowing. So that we will see later on in current electricity. But in our case, for now, they reach a steady state and it stops. But is this story clear, everyone? This is what happens if you put a conductor. Why only conductor? Because if you put an insulator, insulator has a problem. Insulator does not have enough free electrons. If you try to put an electric field, some electrons will go, but that's it. All the electrons have already gone. So you really don't have enough force. So field will not be zero. So conductors are special. They have a lot of free electrons. So we can be sure no matter what you try to do, they'll always fight back. Is the story on this page clear, everyone? Clear what is happening with the whole thing? When an external field comes, the electrons will move. You'll get an induced charge. So when this electron, right, tries to go to the left side, these electrons on the surface will say, boss, don't come here. They're already repelling. This plus is attracting. So now there is a counter force. Clear? Now, so few statements here. So this is what happens. So the field due to the induced charges, so these induced charges will create a new field. So the charges which came on the surface are called induced charges. Field due to the induced charges cancel out the external field. Permittivity of conductors is infinity. What is the meaning of permittivity? Resistance to the external field, isn't it? They will completely resist you. They'll stop you from entering. That is the meaning of permittivity, right? Electric constant. Not at starting. It takes time. Na? Eventually, always in steady state. Clear? That is one point here. Now, some important statements here. The field inside a conductor due to static charge distributions. Now, what I showed you here is a scenario where the field is uniform. The field is not changing with time. Field inside a conductor due to static charge distributions. Static meaning the charges are not moving outside. Is zero. So this is now why is that? Think about it. Let's say if that some charge is outside and this is creating the field, and if this charge moves here, the field will keep on changing. So what will happen? The electrons will try to keep on adjusting front to back, front to back. The field will not be zero. You won't reach a steady state. So this statement, what we wrote, is true for static charge distributions. Meaning, if you take a conductor and if you put a charge Q outside, you can be sure inside the field is zero. But for some reason, if this charge starts going front to back, front to back, front to back, then E here also will keep fluctuating inside. It's like every time it will try to make zero, the charge is already moved. So I have to reach a new equilibrium. So the equilibrium is moving continuously. Instead of a conductor, if you take an insulator, field inside need not be zero. It will be actually less. It won't be zero. We will talk about that later on in capacitors. That's the next chapter. Basically, it doesn't have free electrons. So this story, what we said, the electrons will go and separate. That won't happen. Second thing, if you take a conductor, so just now we pulled the field inside is zero. If field is zero, that means the potential is constant. A conductor is equipotential. It doesn't matter what shape it is, what charges are outside there. It doesn't matter. A conductor is always equipotential. How do we get this? We know E is equal to minus dV by dr. And if E is zero, this implies V is constant. That means for a conductor, since it is equipotential, the field lines will always enter the conductor perpendicularly and leave perpendicularly. Field lines always enter and leave the conductor perpendicular to the surface.
Okay.
All right. So how will this look like? It would look something of this sort. Let's say we got a random conductor here, and let's say we also have a cavity. We'll talk about also cavities in more detailed. Just for an example, let's say we have a cavity here. And let's say outside there is a plus Q charge. If someone asks you to draw the field lines, see what happens. This plus Q here will attract the electrons here. So this will get a minus charge here. How much? We can't calculate this. And this side becomes positive because the whole thing is neutral. The electrons from the right side must have come towards the left side. You're getting why this will happen? Because the free electron here will get attracted towards the positive charge, isn't it? So they'll start coming on the left-hand side. And you start getting a vacancies here. Think of like this. If you're in a stadium, right? And if the show is going on here, won't all the people leave the seats at the back and they try to come to the front to get a better view? So the vacancy of the seats is the positive charge, and the people coming to the front and flocking is the accumulation of negative charge. We got all positive. Now, if you try to draw the field lines here, this is how it looks. So they will enter perpendicularly here. And interestingly, there'll be no field lines inside the cavity because field inside the conductor is zero. That means if field lines can't cross the conductor, then how will you? And there's no charge inside the cavity. You can't get field lines there. To have field lines, you should have a charge. There is no charge here, and the conductor won't let the field lines go inside. We'll talk about that also in some time. But roughly, I hope you got the idea there. Now, here I have a doubt. Why can't you have a situation like this? Since this is a negative charge and this is positive charge, why can't you have some field lines going from the positive to your own negative charge? This is not possible. Can someone tell me why this is wrong? This could be a theoretical question. Yeah, right, Obia. What do you guys other think? This, if you remember, I did say something like this. There are field lines inside already. There are no field lines, right? Conductor hai ye. We know field lines will go from positive to negative. So why can't you have field lines coming from your own body to your own negative charge? What is the explanation that I'll give you? You guys remember the statement? In the direction of electric field, potential changes. So that means if you go from A to B in the direction of the electric field, the potential at B should be less than potential at A. But we said the conductor is an equipotential region, so VA is equal to VB. Therefore, you cannot have field lines going from your own surface to your own surface. Because if you have field lines, there will be a potential difference. This is a very neat way of solving some questions. That one theoretical statement will help you sometimes to avoid all equations. Right? Yeah, conductor is equipotential. So the argument would be this: in the direction of the field line, potential changes. But here we know VA is equal to VB. Therefore, field has to be zero. If you have that field line, it will create a potential difference. All clear with this so far? Now, let me ask you just one question here. When this electron is sitting here, is the external force acting, is the external field giving force on the electron? Yes. Is the induced charge is giving a force on the electron? Yes. But is the net force on there on the electron? No. I hope you're getting the thing. So the net field and the net force is zero. Be careful there. Individually, everyone is exerting force, but the net force is zero. That word is important. So when you say the field inside a conductor is zero, we are talking about the net field, the total. This is due to all charges present in the space, including the induced, external, everything. Due to all charges, external plus induced. Together, they will not create a field inside. Individually, everyone is exerting force, but together they do nothing. All clear with the story so far? This is the main idea that so inside a conductor, the field is zero. This is a and static charge distribution. So we'll play with that only. That statement you have to be convinced and you should be sure about it. Now using that, let's go ahead. Let's see a few cases, and from there I think we can work on it. So if I give a charge on a conductor, so how does that work? Case one. So we'll take different cases and we'll see how it works. We got a conductor, solid conductor, and someone gave a charge Q to it. So my doubt is, can some charge be inside, some charge be outside? Where will this charge exactly be? Now we can prove this mathematically. We can also think about it, but let's see it mathematically first. So this conductor which we have, consider a Gaussian surface. Remember, a Gaussian surface is imaginary. It is just your imagination. So I will consider a Gaussian surface. A Gaussian surface is simply an closed shape where the flux is electric flux is calculated. Right? Now, just now we proved the field inside the conductor is zero. Just give me a minute. Someone is knocking the door. Yeah. So just now we proved the field inside the conductor is zero since it is a conductor. If the field is zero, then integral E dot dA, the flux is zero. If the flux is zero, this implies, therefore, charge enclosed is zero, meaning there cannot be any charge inside the conductor. So you can take now any shape of a Gaussian surface, and we have proved there will be no charge inside a conductor. So charge cannot exist inside the bulk of a conductor. Bulk meaning in that solid conducting material, you can't keep a charge. If you put a charge there, it will disperse. So you can't say, I'm going to put a charge Q here. If you put a charge Q here, for some reason, it flies off. Think about it. Logically, it makes sense. In a conductor, if you're going to take a charge and if you dump a lot of positive charges, what do you think will happen? Won't they all repel? And when they repel, what will happen? They'll try to go as far as possible. And what is as far as possible? The surface, isn't it? So when you put like charges together, they're just going to repel and fly off to the surface. See, when you're putting a conductor, right, you're telling the charge particles, boss, you're free to move here. Here, there is no resistance. No one is there to stop you. You can move wherever you want. So if you put a bunch of like charges, they will just fly off. And the maximum they can go is the surface. That is the farthest they can go. Charge cannot exist in the bulk of the conductor. That means all this charge has to be somewhere, and that can be only on the surface. So the picture will look like this. So if you give a charge Q to a conductor, it will not go inside, it will just stay on the surface. There, that is our case one. Any doubts on this case? So we are slowly building it. What happens if you give a charge and everything? And that statement was important. The field inside a conductor is zero, and that's our mathematical proof there. Logically, also, you can say if you put a bunch of electrons here, they will just repel and fly off. They'll try to stay as far as possible. Any doubts on this page? Shreyansh, Shaurya, clear with this? Pratyasha, clear? Shreyan, Tanishka? Great. Case two. What if you have a conductor with a cavity? Meaning, let's say we have a conductor and we have a cavity inside. And now I'm giving a charge Q again. So my doubt now is maybe some charge can go inside. Who knows? We don't know, right? So we are guessing. So if you have a conductor and if you dump a charge on it with a cavity, now what would happen? Since we don't know what happens, we will assume some charges inside. So we will assume there will be some charge inside. Let's call it plus Q. and there'll be some charge on the outside. There'll be no charge in this solid. We proved this already. You cannot have charge in the conductor. You can only have it on surfaces. And let's say Q minus Q is on the surface because total charge is conserved. If small q is inside, Q minus Q must be outside. Again, we play the same story. Consider a Gaussian surface enclosing this cavity. Field inside a Gaussian surface is zero. Therefore, flux is zero. Therefore, the charge enclosed must be zero. You cannot have charge inside the cavity. That means if you give charge Q from outside, it will just stay on the surface. It will not try to enter the cavity. And logically, ये भी सोच सकते हो. सोचो ना. You took a conductor, you took a cavity, and if you try to put the charges here, plus and plus, won't they repel each other? They have a better option, isn't it? They will try to go away to the outermost surface. They're more happy here. They will try to be as far as possible. So staying on the inner surface is not a good idea. Yeah, if someone is there to catch you, that's a different story. But here, there is no one there, so they will prefer to go on, stay on the surface. Clear with that. So the picture would look like this. So if you have a conductor with a cavity, and if you try to give a charge Q to it, it will only stay on the surface. It will not enter the cavity from outside. This is one good idea there. That means no matter what happens outside, if you're sitting inside the cavity, you don't know what is happening outside. There's a name for this. This is also called a shielding effect. The best example, you must have noticed this multiple times. Did you ever take a phone and get into a lift? When you got into a lift, did you observe signal goes off? Your lift is a metal box, isn't it? When you are talking on a phone, it is an electromagnetic signal. So the moment you get into the lift and the moment the door closes, your signal goes off or it becomes very weak. Observed it? That's because once the door closes, you're inside a cavity and the field lines from outside won't enter the cavity. So your phone does not get a signal. So every time you get into the lift and the signal goes off, what you're experiencing was this. The field lines from outside won't enter a cavity. It's called shielding effect. In chemistry, you must have heard this word called screening effect. The electrons in the oneness orbit, right, will repel the electrons from jumping into a lower orbit. So the electrons will think there's a Z minus one charge on the nucleus, Z effective. So yeah, so charge does not enter the cavity. Charge from outside does not enter the cavity. It remains on the surface. Any doubts on case two? So I'm slowly building up things for you. Like then we are going to just combine everything together. That is how the problems will come. I don't want to do a problem directly without you understanding what is happening with each one. All clear with this? Case three. This will take care of most of the things. Let's say you kept a charge inside a cavity. We have a conductor. We have a cavity. I have taken a random shape. At this time, you kept a charge Q floating in the spacer. Don't touch the conductor. See, if a charge goes and touches the conductor, immediately it will diffuse to the surface. If you touch a conductor, you're gone. The particles will just fly off. So we kept a Q suspended somewhere in the air. This is a neutral conductor. So conductor has no charge with a cavity. So you have taken a case where now what happens if you have a charge Q inside a cavity? Not touching the surface. No. Now we don't know what is going to happen here. So, but we can figure out few things. Again, think of it this. This plus Q, which are electrons sitting here, see these electrons are normally like they're chill. But the moment they see this positive charge, they get attracted towards this. It's like you're an auditorium, right? Or a concert and the music is going on. All the people will flock to the front rows, isn't it? So all these electrons will try to flock to this thing. Now, if all are flocking here, that means you'll get vacancies on the outside seats. So the absence of electrons is called a positive charge. As such, there is nothing called a positive charge. It's all about electrons only. So this plus Q will start attracting electrons onto the inner surface. And these electrons are coming from where? They're coming from the surface. So the surface becomes positive charge. And the inside becomes negative charge. How much? We don't know. So let this be plus Q. Let this be some negative induced charge. This is minus Q. To compensate, because the whole thing was neutral, the outside must be plus Q. This much we can guess. And remember, conductor mein there cannot be any charge. That story is still valid. Now, again, we play the same game. Consider a Gaussian surface enclosing the cavity. So you just have to make sure the Gaussian surface always passes through the conductor, because the field inside a conductor is zero. So that's your Gaussian surface. Field is zero, therefore flux is zero. That means the charge enclosed, which is Q minus small q, is zero. Therefore, Q is equal to plus Q. There, we proved something here. If you put a charge inside a cavity, no matter what kind of cavity, no matter what shape you take, you will always induce equal and opposite charge. You're getting it? Till now we couldn't prove this. Abhi dekho, when I kept a charge Q like this, if you ask me what is this minus Q, I don't know. You can't calculate this. There is no way to calculate this small q. But for the first time, we can calculate actually. If you put something in a cavity, you will always induce equal and opposite charge on the inner surface. So if you put a plus Q here, you will induce minus Q on the inner surface and plus Q on the outer surface. That is how keeping charges inside a cavity behave. Any doubts on this page? Now let's take a few more examples on this to get a little more idea on this. Now, how will this distribution happen? If you take a symmetrical shape, you get a symmetric distribution. If you take a non-symmetrical shape, you get a non-symmetric distribution. Example, let's say if you take a solid sphere, right? And if you take a random conductor, let's say random cavity, let's say for symmetry, let's take a circular only, let's say circular cavity. And let's say you kept a charge plus Q exactly at the center. So how will the distribution look like? Because it's exactly in the center, by symmetry, the inside charge we proved it should be equal to minus Q. We get a uniform distribution. It will pull equally on all sides. This would be plus Q, which is uniform. And you will get a minus Q on the surface. That is also uniform. You might think like, oh, sir, why is the outside one uniform? Isn't this plus Q closer to this surface? Now tell me one thing. For this charge to interact with this charge, remember the whole story? How do two charges interact with each other? Through field lines, isn't it? Is there even a single field line going from inside to outside? If you try to draw the field line, see how they look. The field lines will start from the plus Q. They will stop at the surface. All the field lines will vanish at the surface. That means none of the field lines from inside will not go outside. That means the charges outside does not know who is there inside, isn't it? Because the way two charges communicate with each other is through electric field lines. And if there are no field lines, they'll not know what is inside there. So the field lines inside the cavity do not go outside. That's one important thing. This is what I was calling a shielding. So the outside people don't know what is inside, inside people don't know what is outside. So this metal in the middle, the conductor, is blocking all the field lines. So there's no way of communicating. Think of like this. It is like someone kidnapped you and put you in a soundproof room. There are people outside the room, but no matter how much you shout, the voice never goes out, so no one knows you exist inside. You're there inside, I'm there outside, you're shouting, but because I can't hear you, I can't come to help you. As simple as that. Because all the field lines are blocked inside. I know, bad example, but works. Clear with this. So the field lines from inside the cavity. So that is the reason the outside charge will think what? Okay, I have a minus Q, and that's it. There's no one to stop me from doing anything. So I will just spread it uniformly because the surface is symmetrical. Field lines from inside, right? Inside the cavity do not come out because the conductor is blocking the field lines. Therefore, charges outside are unaffected by charges inside. This is pretty useful statement later on. Are unaffected by inside charges. Now, again, be careful when I say inside cavity, what charges are we talking about? We are talking about that plus Q and that induced charges on the surface. Induced minus Q on inner surface. And just to be little more clear, if I ask you this question, this plus Q in the center, is this plus Q interacting with this minus Q? Yes or no? They're interacting. Two charges will always interact with each other. This induced charges plus Q, is it interacting with this minus Q? Yes, it is interacting. But together, they don't interact with anyone. Are you getting the statement there? Individually, they're interacting. The plus Q at the point charge is interacting with outside. The minus Q induced is interacting with outside. This was a minus Q, sorry. Interacting with outside, but together, they don't interact with anyone outside. Because when you take them together, the field lines will vanish on the surface. Is this statement clear, everyone? Let me take one more example. What if the outside is uniform? Let's say we have a spherical cavity and we have a random cavity. We have two cavities. And let's say here we have a Q1 charge. Let's say I don't keep it at the center. I'm keeping it little to the side. And here, let's say I keep minus Q2. I kept plus Q1 and minus Q2. Now, if I ask you to draw the field lines, the distribution, it looks like this. I'll just draw a big one. Now, because this plus Q1 is not in the center, it will attract the electrons closer to the surface. So here there will be a lot of accumulation. Here the accumulation will be less, but the total will be still minus Q1. This will be non-uniform. If you don't keep the charge in the center, you'll get a non-uniform distribution. This minus Q2 is anyway in a random surface, so you will anyway get non-uniform, but this time you'll get a plus Q2. This is also non-uniform. But because the conductor is neutral, on the outside surface, now we will get a charge which is Q1 minus Q2. Again, depends on who is bigger. I'll assume Q1 is greater than Q2. We will get a plus charge, assuming Q1 is greater than Q2. And again, like I said, this Q1 minus Q2 does not know that there are cavities inside. So outside surface is uniform. This will be uniform distribution. No matter what happens inside the cavity, the outside charge doesn't care. Getting it? And if I try to draw the field lines, they will look like this. So here you'll get a lot of field lines, a bunch of field lines like this. Here the field lines will spread out little thin. They would look something like this. I didn't draw it that great, but yeah. Here also field lines will look something like this. So in this case, they'll be coming from here. This is how the field lines will look. And this outside field lines will again go out like this. This will be perpendicular. All clear with the story? So when do you get non-uniform outside? If you want non-uniform outside, we have to create a non-uniform surface. Let's say we take a circular cavity and you take a non-uniform surface. Now, if you put a plus Q charge again at the somewhere here, center, this will create a minus Q. This would be uniform because the cavity is uniform, but the outside charge will be non-uniform because the outside surface is non-uniform. So yeah, it depends on your charge distribution and your type of the surface. Are all these examples clear, everyone? Any doubts on this? There, we started with the field inside a conductor is zero, and we developed all these things like how does giving a charge to a conductor will make things clear. And let me add one more point here. Imagine we have a scenario like this. Let's say outside we have a charge Q1. Inside we have a charge Q2. This Q1 here will induce some negative charge here. How much? Remember, you can't calculate this. You can calculate only inside a cavity. This will be some plus Q. That will be equal and opposite. For now, I'm ignoring this Q2 distribution, okay? Now see what happens. All the field lines from Q1 will come and stop at the surface because that minus Q is absorbing. And all these field lines will again go from here. That means if you look at Q2, the Q2 does not know that there is someone outside. The plus Q2 plus Q1 and its induced charges. So Q1 is inducing which charges? Minus Q and plus Q together, all these three of them together. Do not interact with that Q2 inside the cavity. Together, individually they do interact. Because force between two charges is independent of medium. Do not interact with charges inside cavity. That means if I write this in a vector form, the force between Q1 and Q2 plus force between Q2, the plus Q and minus Q together, this sum is zero. Are you clear with this? So if I ask you this question, is this plus Q1 repelling Q2? Yes, the Q1, Q2 are repelling. What is this minus Q doing? This minus Q is attracting. This plus Q is repelling. So this force and this force are cancelling out. Are you clear with this? What happens if they don't cancel out? If they don't cancel out, that means some field lines are entering the conductor and reaching Q2. If the field lines enter a conductor, you know what happens? The electrons will start moving immediately. They'll create new charges till the field gets cancelled. That's the story you should know. If the field lines enter a conductor, the electrons will start moving in such a way, they will cancel that field. Until they cancel the field, they won't sleep. They'll keep fighting with that field. This phenomena, right, is called shielding effect. The same thing we can say about inside also. So charges inside the cavity are shielded from outside effects. So when there's a thunderstorm and you're sitting in a car, the sitting in a car is actually the best thing to do. By chance thunder hits the car, it will flow from outside and goes to the surface. If you actually start coming out and running on the road, and if the road is flat, you are the tallest surface there, it will come and hit you. Technically. All clear with the story. So we started with the story field is inside a conductor is zero. Then we gave some cases. You cannot have charge inside a conductor. Metal may you cannot have bulk of a conductor. If there is a cavity with no charge inside, no matter what you give from outside will stay outside. Then we said case three, what if you have a charge inside a cavity? Then you'll get an induced charge on the inner surface and there'll be an outer surface. How will the distribution occur? It depends on the type of the surface. Is it a uniform or non-uniform? Is the charge at the symmetrical surface or non-symmetrical? So we took few examples and the shielding effect. All clear with this? Let's see some questions. That will make things more clear. Let's start off with something simple and then we'll slowly bomb it up. Let's say we have a conductor. We had a cavity. Solid conducting sphere with cavity. This is your center. This is your charge Q2. Here we have a charge Q1. This distance is D and this distance is Z. This point is A. A is a point on the surface. A is the radius of the sphere. First thing, draw the charge distributions. Roughly, how will the charges will look like? Second thing, find force between Q2 and induced charges on inner surface of the cavity. Find potential at the center. Find potential at A. Due to conductor. And let me give you let's say this distance is some y. Hmm. Let's get the first two parts. I dumped a lot of things. We will solve them one at a time. Roughly draw a chart distribution. I'll draw it. I'll show you. See if you got the same thing. Okay, let's see. Let me show the chart distribution. Now there are a lot of things, so listen carefully. And you should definitely do this again on your own. And these are not tough to solve, but it's a lot theoretical. Like if you really don't understand your three concepts there, it looks weird. Okay. So let's see the distribution. There are multiple things happening here at the same time. So let's see one at a time. I'll just draw a bigger version of it. Let's start from inside. So this Q1 here is not in the center. So this will create some non-induced, non-uniform charges. How much? Minus Q1. That much I know, but it is non-uniform. There'll be more minus here, and that is that. This minus Q1 will come to the surface because, see, remember, when you say minus Q1, meaning electrons from the surface got pulled inside. So you will get a plus Q1 outside because the conductor was neutral. So this will create a plus Q1, which will be uniform. Great. Now, this guy Q2 outside will create a non-uniform charges. So on the surface, which already has a uniform, you're coming creating a non-uniform. So uniform plus non-uniform, the whole thing becomes non-uniform. It's messed up. How much? Minus Q. What is the value? We don't know. You can't calculate this. This would be plus. So the outer surface has become non-uniform because of that Q2. There. That's your chart distribution. Clear with this. So if someone asks you about the chart distribution, you just show this and you're done. You can't do anything more than that. Outside will be non-uniform. Now, second part. Find the force between Q2 and the induced charges on the inner surface of the cavity. Let's see that part. Right, Samyak. Now let's take this picture there. So when you say conductor, let's make it clear, okay? I'll separate it for you. When you say conductor, how many things are there? We actually have this guy, this guy. So we have one uniform Q1. So when you say conductor, it can be divided into three parts. This one, Q1 uniform. And then we have minus Q non-uniform and plus Q non-uniform. And we have a non-uniform minus Q1 in the inner cavity. So when I combine these three, isn't this the conductor? This is a charge distribution on the conductor. So you can divide them into three different shells for convenience. Like it will be more easy to see what each one is doing. on the conductor. So basically two charges on surface and one charge inside the cavity. Okay. So roughly that's what happened there. Now let's see what is being asked and let's try to work out from there. You are asking find the force between Q1 and Q2. Great. So let's talk only about that guy. I will take the cavity. You're only interested in the cavity, so I will not draw the outside charges. They are there. Now let me ask you this question. When you took this charge Q1 here and you induced a minus Q1 non-uniform here, all the field lines from here will simply get absorbed by the inner surface. Does this charge outside which is there, Q2, does Q2 know that there is someone inside the cavity? Right? Q2 does not see any field lines coming from inside the cavity. So Q2 will say, inside to kuch hai hi nahi. If there's something, there would have been some field lines. Therefore, so from Q2 ka argument, the force between Q1 and plus Q2 plus force between Q2 and the minus Q1, which is induced, that sum must be 0. Now think about this logically, right? Because of this non-uniform distribution, you cannot find the force directly. We don't have a formula to find force on a charge due to non-uniform distribution. But we can use this argument to prove it. And what is the force between Q1 and Q2? That distance is d. So this is k Q1 Q2 by d square. This is the force between Q2 and the induced charge minus Q1. Q1 and Q2, the force will be minus of k Q1 Q2 by d square. So if Q1 Q2 are repelling, then this negative charge will push this thing towards Q2. Are you clear with this? This is how you calculate this kind of stuff. And this is what I was saying. There'll be no calculations, no equations. You have to use arguments because this is happening this way, it will be this way. Any doubts on this? Now, can you try the third one? How do you find the potential at the center? Zero. Okay, let's see. The potential, again, remember, when you say potential, luckily, right, it doesn't have a direction. It is a scalar quantity. Aditi got something. Okay, let's see. We need to find the potential due to everyone, right? Now, who is everyone? Let me take these guys. Let's see who is everyone. So there is one charge on the outer surface. There is the induced charge on the outer surface. We have our cavity here. So for convenience, I'll do one thing. I'll draw the whole thing and then I'll draw the cavity. Right? And we have our Q2 also sitting outside. Perfect. Now, what are you asking? You're asking to find the potential at the center. I'll just call it C. And remember here, this guy will be what? Q2. You will have a non-uniform distribution minus Q2. Perfect. And what is this distance? This was Z. Okay, so that means if I can calculate the potential at the center due to Q1, due to these two, and due to Q2 minus Q2, and due to this Q1 yeah, outside. Yeah, sorry, this is Q1. Perfect. And you're getting? So if you want to find the potential at the center, you have to find due to Q1, Q and minus Q, Q1 minus Q1, and Q2. If I find due to these four things, won't I get the potential at the center? Do you guys agree with this? Because potential is a scalar quantity, find the potential due to all charges. Perfect. What is the potential at the center due to this guy? For a hollow spherical shell, the potential inside is kq1 by r. R is the radius. Now this is interesting. I don't know small q, I don't know minus q. The charges are non-uniform, but luckily everyone is equidistant. So potential at the center is k q minus q by r, which is 0. These charges will not create any potential difference. What about q1 and minus q1? Again, same story. The center thinks there is no charge there because there is no field lines coming from there. Center does not see any field lines from inside. Right? So if there are no field lines, then integral E dot dr is 0. That means potential at infinity, and here is 0. So it will simply think there is nothing inside. So therefore, it thinks there is no charge, even though the minus q1 is non-uniform. That is the whole part. Technically speaking, you can't find due to minus q1 because it is non-uniform. It thinks, right? There is no charge inside. That's a very neat trick, like the shielding effect. Therefore, this VC is also 0. You cannot find due to Q1 directly because I don't know the distance. You cannot find due to the inner surface directly because the charge is non-uniform, but together they will be 0. Is this making sense, everyone? That's a very important thing. We keep using it multiple times. So, and then what about this point charge? This point charge will say, okay, VC will be KQ2 by Z. Perfect. So what is the potential at the center? Add all of them. So potential at the center is kq1 by r plus kq2 by z. That's your answer. Have a look at this. If I can find the potential due to all the charges in the space, isn't that the potential at the center? Are you clear how we played this with each step? So the main thing is the charge distribution. If you don't know how the charges are distributed, you won't be able to handle the potential calculation. Making sense? Little confusing. I think you are understanding, but yeah, it is going little like, about theory hai. You have to keep drawing pictures and seeing and everything. Question still not over. We need to find the potential at A due to the conductor. Now, the word is important. I didn't ask you the total potential. Total potential, now your life would have been easy. You know why? Can someone tell me what the total potential at A? Where is A? On the conductor. What is the potential of the conductor? Same everywhere. So potential at the center is the potential at A, isn't it? Because both are on a conductor. So the total potential was the easiest one. Yeah. So we can also say VA net is equal to V center. Why? Since both are on a conductor. But I didn't ask you this question. What did you ask then? You asked this thing. You want only due to the conductor, meaning you don't want this Q2. You don't want this Q1 also. So if I draw the cavity here, this non-uniform is there. Bus. You don't want Q1, Q2. Now you're asking find the potential at point A due to these three people. Okay with this. Now what I can do actually reverse. Instead of finding due to these three people, what I will do, if I take Q2 here, Q1 here, and if I take Q2 here, right, I'll take due to everyone. This distance will be how much? This radius was R and that was Z. So this distance will be R minus Z and this distance was Y. Okay? Now listen carefully. So the potential at A due to this guy, so V due to Q1, this is V due to Q minus Q, this is V due to Q2, V due to minus Q2, and V due to Q1, the five of them. So that would be V due to plus Q1 outer surface plus V Q and minus Q outer surface. I don't know how much is this because I can't calculate it. Center was lucky because center was equidistant. A is not equidistant. This would be V due to plus Q2. That is point charge. V due to minus Q. That is on the inner surface of cavity. Plus V due to plus Q1 charge. This must be potential at A net. This value I already know from here, which is K Q1 by R. I'll just erase this. You understand this thing. So this is K Q1 by R plus K Q2 by Z. Perfect. I know due to this guy also. K Q2 by Y. Remember, potential is a scalar, so direction matter nahi karega. I know this guy also. K Q1 by R minus Z. What I don't know is this and this and this. But what was asked in the question is the field due to the conductor. That is these three only, isn't it? Is that making sense? These three are the field due to the conductor. Because this is on the outer surface, this is on the outer surface, this is on the inner surface. If I add all these three, that should give me the field on the conductor. So these three things here, this is the potential due to the conductor. You cannot find it directly due to each one, but I know the total, I know the remaining two, I subtract them, I'll get the answer. So potential due to the conductor will be KQ1 by R. This will be pretty good advanced paragraph questions, right? KQ2 by Z minus KQ1 by R minus Z minus KQ2 by Y. So what I did, I know the total, I know due to Q2, I know due to Q1. So if I subtract Q1 and Q2 from total, whatever is remaining must be the conductor. Is that argument making sense? Definitely do this again after the class today or tomorrow. I'll ask you one more like this. We will see one more question like this, and I think that should give you a little more idea there. But you saw how we played around. Gauss law में questions ऐसा होता है. Did you see any big calculations? But it is all arguments, right? It is this, it is that, this. So we are just playing like that. Take a break. Come back in 5 minutes. We'll continue from here. Yeah. Right, Samyak. Take a break. Come back in 5 minutes. We'll see. So let's go ahead. Let's do one more like this. I think you got the hang of this. I think then we are good to go. We got a conductor, we got a cavity. We have a charge Q1 here. We have a charge Q2 here. Q2 is at the center of the cavity. Mm, So from center to here, this distance is smaller. This center, now let's call it O. And let's call this thing O dash. So O2 here, this radius is capital R. From O to Q1, this distance is some D. There is a point A here. A to Q1, this distance is Z. There is a point B here inside the cavity. That distance is Y. Hmm. Maybe I should put the charges ka different color. Let's put Q1 and Q2 so that the green ones are the charges, the red ones are the points, and O and O dash are the centers. So the question is find the potential at OAB. So let's start with that. Cavity O is the center of sphere. O dash is center of cavity. Potentials are little easy because they don't have a direction. Fields will always get messed up. Find the potential at O, A, and B. And find potential at A only due to the conductor. This is a solid sphere with a cavity. There, let's get this thing. You got this, then you get the hang of this whole thing. What we did today was for this question. These are the kind of things they'll frame. Definitely spend some time tomorrow, take a rough paper, solve each and every question, go through the notes. If you do it as early as possible, the better. You will get the hang of it. You wait for 3-4 days, everything will start looking weird. So you just have to get it cleared once, and then after that, it will feel manageable. K1 by D, K2 by R. Hmm. Right, Samyak. You got the A and O. Try. First, try to put the chart distribution. Draw the chart distribution roughly कैसा दिखेगा. Start from there, and then I think you'll be fine. Right, Arya. Okay, let's see. B is an interesting one, though. See, let's draw the chart distributions. Let's start from inside. This Q2 in the center, it is exactly in the center, so it will create uniform distribution minus Q2. And that Q2 will come to the surface. That will also create uniform distribution. So you talk one charge at a time, like don't worry about what the other guy is doing. This also will be uniform. So when you say conductor, all these things will come. And this guy, which is Q1, will induce a non-uniform. So if you see, kind of looks like the same thing as what we did in the previous one. This is plus Q. Great. So the whole outside becomes non-uniform. Perfect. So when someone asks you what is the distribution, technically you can divide the whole thing into a Q1 uniform distribution, Q2, sorry, Q2 uniform plus Q minus Q non-uniform. We have a point charge plus Q2, and we have a minus Q2 uniform, and we have that Q1 sitting outside. Perfect. These are all the charges that you have. So if someone asking you the potential, if you can find due to all these guys, your job is done. Center is the easiest one. Always remember, center is the easiest one. Why? Because at the center, this minus Q and plus Q are equidistant. They'll always come zero. Perfect. So this guy will give the potential KQ2 by R. This will give zero. Basically, the total sum of the charges is zero. They both of them together will not interact. So this would be zero. No field lines from inside. But luckily here, you can actually find them also, because it is uniform. What is the potential difference? KQ2 by this distance, isn't it? And for a uniform shell, you can put a minus Q2 charge at the center, so the both will cancel out. And what was this distance to see? That was distance D. This is KQ1 by D. Done. So potential at the center is KQ2 by R plus KQ1 by D. This is also the potential at A because they're on a conductor. That's the best thing about the conductor. You can always find at the center and you can always argue, boss, it's an equipotential surface. How do you find VB though? VB is a little interesting. So see, there is no way you can do VB directly. You can't get in, but we can do something like this. So this was the cavity there. Now inside, the only reason you're getting any field lines is because of Q2. All field lines inside the cavity are because of Q2, because this minus Q2 will not create any field lines. So here, the field lines inside the cavity, if you take a distance x, the field is KQ2 by x square. So then I can do this. Your B is somewhere here. Your A is somewhere here. This distance was y and this distance was r. Then we can write potential difference VB minus VA is equal to minus integral E dot dr. We use the electric field into potential difference. So B is the upper limit, that is y, and A is the lower limit, that is r. So that would be minus KQ2 by x square dx, limits from r to y. That would be plus KQ2 by y हो जाएगा. That will be KQ2 by x, limits r to y. That is KQ2 by y minus KQ2 by r. This is the potential difference between VB minus VA. And VA, though you already know. VA is this guy, KQ2 by R, plus KQ1 by D. This is your VA. KQ2 by Y minus KQ2 by R. This is the field inside the cavity. Because the field inside the cavity is only due to Q2. No other charge will create field inside. Because outside lines will not enter. Then you might ask, sir, what about this minus Q2? This minus Q2 is a uniform distribution. What is the field inside a uniform shell? Zero. Are you clear, everyone, how to get VB? You cannot get VB in any other way because we don't know the distances from outside and all that thing. But since I know the field ka thing, I can play from there. Any idea still here? Any doubts still here? All got this? There's still one part of the question. You want to find the potential at A only due to the conductor. Again, same story. You want to find at A. A is somewhere here. So potential at A net, which I know already, is due to this guy, KQ2 by, I'll just write like this, potential due to Q2. Outer surface, potential due to minus Q plus Q. Outer surface, potential due to minus Q2. Inner surface. These three is the conductor. plus V plus Q2, the charge, plus VQ1, the charge. This guy is simply KQ2 by small r, that's the distance, and this guy is KQ1 by, what was that distance? Z. And what was this guy? KQ2 by r plus KQ1 by d. There you know everything. Substitute, you'll get the potentiality to the conductor. Are you clear with this? I'm sure it feels like, it looks like we understood, but something looks weird. You should do it again. That is when it will get cleared. When you get stuck, please, you can just go back, refer, and see where you're doing wrong and come back again. All clear with this? These are one of the toughest ones in Gauss law. Not because there are a lot of calculations, there are a lot of arguments. But I hope you got the theme by now, what is happening. Any confusion in this? Anyone not clear with anything particular here? Please ask. Aditi? Anvita? Obia? Clear with this? Vedika? Trishi? Param? Arya? Ishman? Samyak? Naisha? Clear with this? Shaurya? Tanishka? Utsa? Clear with this? Perfect. Next thing. Earthing or grounding. What is earthing or grounding? So when a conductor, you must have heard this word, right? This is an earth wire karke. Or if you ever seen your plug, right? There are three holes. Technically, power comes only in these two holes. The third one is called an earthing. It's actually a safety mechanism. Basically, when a conductor is connected to the earth, the potential becomes zero. So by chance, if there is any short circuit in the device, and when you touch it, instead of you getting the shock, the current goes to the earth, so you are safe. So that's the whole idea there. But most of the time they don't work. In in apartments and all, maybe they will work. But if you're in a small society, right, it doesn't work because the grounding, right, you have to take a 1 to 2 meters long copper rod. You have to dig a big hole. Then you have to fill it with some kind of a, sodium bicarbonate, some material. I forgot what it is because soil is not a good conductor. So you have to put some conducting material between this and the soil, and then you have to give the connection to the house. A 1 to 2 meter long copper rod, right, is expensive, right? So what people normally do, they dig up the hole, they steal the copper rod and sell it off. That's one of the most common phenomena in rural areas. That's more profitable. Meaning a 2 meter long copper rod will easily fetch you 4 to 5,000 rupees, right? Smart, hai na? And that to see, it is just outside of the house. Just go dig a hole, take the rod, go home, and you're done. The thing doesn't work. Anyway, if you're putting solar panels on your house, they'll expect you'll have earthing. If you don't have earthing, they'll install it and go. So when a conductor is connected to the earth, its potential becomes. So instead of copper rod, then you use something more cheaper, like a steel rod or something. Might not work well, but something is better. Or you can have a dog in the house which can go and bite the people when they come to steal. So, and again, it should be a local Indian breed dog. Huh? If you get nice husky and all, they'll take that dog also and go. Yeah, so that's also profitable, right? You have a husky there, you can catch it and sell it off. That is more profitable than a copper rod. So get an Indian local dog. No one will steal it. It is more safer. And they're not bad breed anyway, but it's what equal to the potential of the earth. Now, technically, right, earth ka potential is slightly negative, right? But for convenience, we take it to be zero because you can define anything as zero. It doesn't matter. So this is the symbol for grounding. So one line and something like this. You'll have three lines here. So this is the symbol. You see the symbol meaning it is grounded. What happens when you ground something? Potential becomes zero. That's it. It does nothing, no magic tricks, nothing. The potential of the shell becomes zero. One important thing, because you're grounding, charge is not conserved because charge can go into the earth or come from the earth. So you get an information potential is zero, but you lose an information charge is not conserved. Clear? That's it. That's about grounding. So if you ground something, potential becomes zero. Now let's see some questions on shells. These are good ones. Let's start off with something easy and then we'll slowly bump it up. So we got a shell and then we got one more concentric shell and we got a switch. This radius is R. This radius is 2R. Concentric conducting shells. Let's say this thing has a charge of plus q and this thing has a charge of minus 3q. And this is your switch. Find the charge distribution before and after closing the switch. Before closing the switch, how will the charge distribution look like? Once you close the switch, how will the charge distribution look like? Think for a minute or two, then I'll show you the before thing and then I'll show the other one. You might think like, oh, how do we think of, see, think about this thing. You can think of actually, right? This whole thing is like a cavity. It is just a thin conductor here. So basically there's a material here. So that story is still valid. If you have a charge q, you'll always induce an opposite charge on the facing surface. But anyway, give it a try for a minute, then I'll show you. Okay, let's see. Listen, this is important, huh? So before closing the switch, so let's understand this. If you got this, then you'll get the rest of the things. Let's start from inside. Always, when you see cavities, generally start from inside. How much charge you have inside? Plus q. So ask yourself, if I give plus q charge inside, can it go inside? Can it cross that? Even though the conductor is thin, I agree, but can it pass through the conductor and get inside? It can never do that. So this side is zero. So the question has become like this. There is a conductor which is hollow. Someone gave plus q charge. What happens? It stays on the surface. Are you clear with this? If you still have a doubt, then we argue like this. Consider a Gaussian surface passing through the shell. A very thin Gaussian surface passing through the shell. Since it is passing through the shell, field is zero. Therefore, flux is zero, charge is zero. So there will be no charge on the inner surface of the inner shell. Great. Next thing, if this is plus q, the facing surface will always induce a minus q charge. This we proved. Again, if you have a doubt, again we say the argument. Consider a Gaussian surface passing through the outer shell. Since it is passing through the conductor, field is zero. Therefore, flux is zero. So charge enclosed must be zero. So in a spherical cavity or any kind of cavity, whenever you put a charge, you induce equal and opposite charge. Perfect. If this is minus q, we know outside is total minus 3q. So the charge must be conserved. Minus q is already inside. The outside will be minus 2q. Are you clear how I got this distribution? This is important, everyone. Please ask me. So this is how the charges will be. So the opposite faces will always have equal and opposite. And the outer one, the charge should be conserved. So it should be minus 2q. Any doubts on this? Clear? Next thing. What happens if you close the switch? Once you close the switch, maybe some charge has gone outside. I don't know. So this will be still zero. Let the charge be small q. Why? Because I don't know how much charge has gone outside. If this is small q, this has to be minus q. There is no doubt about it. Facing surface will have equal and opposite charge. Let the charge be x in here. Now the total charge must be conserved because you connected them with a wire. Total charge is still constant. How much is total charge? Plus q minus 3q. But this should be also equal to x minus q plus q is minus 2q. Therefore, x is equal to minus 2q. So I proved what is the charge on the outside. I didn't take some random number. Perfect. Any doubts on this? I still have to find small q. If you connect two conductors with a wire, what happens? The potential becomes same. So this point A and this point B, the potential is same because they're connected with a wire. Now listen carefully here, everyone. How do I find the potential at A? If you look at here, these all are just shells, isn't it? So ask yourself a question. For this Q charge, where is point A? On the surface. What is the potential on the surface? K Q by R. So you just have to use potential due to a shell formula. Great. For minus Q charge and minus 2Q charge, both are on the same distance. Right? Where is the thing? It is inside. For these two charges, point A is inside. What is the potential inside a shell? K minus Q minus 2Q by 2R. Is that making sense, everyone? Is equal to potential at B. Now for this small q, where is B? Outside the shell. So what is the formula? KQ by distance. For these two charges, where is point B? On the surface. So what is the formula? K minus Q minus 2Q by 2R. That's the potential at B. This is potential at A and this is a potential at B. You can clearly see this term and this term cancels off. You end up with KQ by 2R is equal to 0 and we get Q is equal to 0. That means when you connected these two things, none of the charge was inside, everything went outside. And it kind of makes sense. Because you're telling the charges, boss, you have a way to go outside. If you stay inside, you will repel more. So better you get out and stay far. It's like you're giving them a gateway to get out. So the charges will be like this 0, 0, 0, minus 2q. That's your final answer. Is this clear, everyone, how we did this? This question can be done in a much easier way. Listen to this logic. If there is a plus q and if there is a minus q, that means there will be field lines here. If there are field lines, that means this point and this point will have a potential difference. But you said they're connected by a wire, meaning you can't have potential difference, means you can't have electric field, you can't have this charge, therefore q is 0. Did you see how we solved without writing a single equation? If there was a small q and minus q, there will be an electric field between the two shells. If there's an electric field, there'll be a potential difference, but you connected them with a wire, so you can't have potential difference. Therefore, small q must be 0. All clear with this? But this is how you solve. Let's see one more like this. Now you guys give it a try. You understood how to handle the shells. This would be a important question, standard mains question. Shell, we have a shell. This is being earthed. So the inner shell is being earthed. This is radius r, and to remember, whenever you earth something, uska potential becomes zero. That's the whole idea there. So this charge is 2q and this charge is q. Find the charge distribution when the switch is closed. Give it a try. If you connect something to the ground, two things happen. One, potential becomes zero. Second, charge is not conserved. So be careful. You cannot conserve the charge once you ground something. Okay, let's see. Should I show you? Let's see. The first thing is the charge distribution. So the moment you ground this, what is the charge on the inner shell? The first thing you should say is, I don't know. Initially 2q hai, I don't care. Because once you ground something, the charge is not conserved. So that initial 2q was useless. So the first thing you should say whenever you ground something, what is the charge? I don't know. That's it. You don't know. That's it. So, but if this is q, this has to be minus q. This we have proved it. Grounding, no grounding, this will not care. If you have a doubt, ऐसा क्यों हो रहा है? You will start with an argument. Consider a Gaussian surface passing through the outer shell. Since the Gaussian surface is inside a conductor, field is zero, flux is zero, so total charge inside must be zero. Therefore, it should be equal and opposite charge. So anytime you feel like why, that's the statement you keep telling yourself. Perfect. And what about the outside charge? Remember, the outside is not connected to anyone, so the charge is still conserved. So this is plus q, and you have a minus q here, so this would be q plus q. So the total charge outside should still be plus q, that is still conserved. Any doubts on these steps? All clear? And then if you look at this point here, VA, potential at A is zero because it is grounded. What is the potential at A? It is due to this one, and this one. Find the potential due to all the charges. For the inner shell, A is on the surface, so KQ by R. For the outer charges, both of them are on the surface, Q plus Q minus Q, and the A is inside, which is 2R. The total charge on the outer shell and point A is inside. K and R will cancel off. This will be Q plus Q by 2 is equal to 0. Q is equal to minus Q by 2. That's your answer, everyone. That is how you do grounding cases. So when you grounded this, the charges have become minus Q by 2 plus Q by 2, and this is Q by 2. All clear with the distribution? Quite a common question in mains. They do ask this kind of things a lot. Again, if you see, once you know how to get the distribution, it is just one equation. Clear with this? Let's see one more like this. I think if you got this, then you got the shells. Three shells. Radius r, radius 2r, radius 3r. You made a small hole in the middle shell and you let a switch pass through like this. So this is S1. And we have one more switch here for the middle shell that is grounded. So you're connecting shell 1 and shell 3 and you're grounding the shell 2. And this charge is plus Q, this charge is minus 2Q, and this charge is 3Q. Now, this could be a good matrix matching equation. They can say S1 is closed, S2 is open, S1 is open, S2 is closed. They can do all that thing. Let's find the charge distribution when both the switches are closed. This is a concentric conducting shells. Find charge distribution when S1, S2 both are closed. Get this thing. You got this thing, you understood shells. They generally don't go beyond this. We'll see the shells again in capacitors though. So the ending of Gauss law is the beginning of capacitors. Again, the same story. You're connecting 1 and 3. So 1 and 3 का potential same होना चाहिए. The second shell you're grounding, so उसका 0 होना चाहिए. That was the whole idea. Try. I'll give 3-4 minutes. Calculations are a little messed up, but yeah. It's a little lengthy to solve, but it's a good one. And you're not clear with the picture, ask me. Step 1, start with the charge distribution. I'll help you with the chart distribution, see whether you got the same. Without putting the proper chart distribution, you can't go ahead. So you connected these two with a wire and you grounded this thing. Great. What is the charge on the inner shell? We don't know. Why? Because there is a wire, some charge could have gone outside. So if this is Q1, this has to be minus Q1. That we can know. What is the charge on the second shell? We don't know. Why? Because it is grounded. If this is Q2, this has to be minus Q2. What are the charge on the outer shell? I still don't know. Let it be X. I actually know nothing on any of them. Great. So let's start finding them. So let's start with X. The charge on shell 1 plus shell 3 is conserved because they are not grounded. That should be Q plus 3Q. That is the charge on the inner and the outer shell. But how much is this? So charge on the inner shell is Q1. ये तो 0 है. Minus Q2 plus X is equal to 4Q. There I got X ka value. So that's 4Q minus Q1 plus Q2. This is the first step. Then what will you say? Define 3 points A, B, C. So this is A, this is B, and this is C. Since A and C are connected by wire, VA is equal to VC. That will give you one equation. VB is equal to 0. That will give you second equations. Two equations, two variables. Can you do this now? You know how to find the potential due to shells. Solve. I'll give 2-3 minutes to solve. You have to get the numbers. Exam, they're going to ask you this. And there, if you just write the equations and sit there, nothing will happen. And that's why people complain, sir, silly mistakes or exam. That's because you guys don't solve only. At the home, when you're practicing a material, you should solve till you get the final number, whether you like it or not. 8 cube 11, 24. Right हो गया, you got it. Yeah, one answer नहीं सम्यक. Answer में 11 आएगा मतलब. Yeah, it's not a great answer. I'll give one more minute and then I'll show you. Just have to write the equations. Okay, let's see. So let's start from here. Potential at A is equal to potential at C. So where is point A? A is inside for all of them. So that would be K Q1 by R. The second shell ka charge is Q2 minus Q1. Please check your equations by 2R. The third will be K. This total charge Q2 and Q2 will cancel. 4Q minus Q1 by 3R. This is the potential at A. This is equal to VC. That would be KQ1 by 3R. KQ2 minus Q1 by 3R. So C is outside for all of them. So you can directly take the total charge by the radius Q1 by 3R. This term and this term goes off. K and R goes off. Then you end up with Q1 plus Q2 minus Q1 by 2. Q1 by 3 plus Q2 minus Q1 by 3. Check your equations there. So that would be your one equation. If you simplify this would be Q1 minus Q1 by 2. That is Q1 by 2 minus Q1 by 3. Q1 by 3, Q1 by 3 goes off here. That's also great. Perfect. Then you end up with Q1 by 6 is equal to minus Q2 This would be q1 by 2 is minus q2 by 6. Then we get q1 is equal to minus q2 by 3. This is the relation between them. That's one thing, everyone. Second thing, potential at the center, the B. VB must be 0. Now for B, Q1 is for Q1 B is outside. K Q1 by 2R. For Q2 and Q1, it is on the surface. So K Q2 minus Q1 by 2R. For these two, B is inside. So you just have to keep asking, is the point inside on the surface or outside? And then use the appropriate potential ka formula, 4Q1 by 3R is equal to 0. K and R goes off everywhere. Q1, Q1 goes off. You end up with Q2 by 2 plus 4Q by 3 minus Q1 by 3 is equal to 0. Take your Q1 here, dump it in this. So Q2 by 2 plus 4Q by 3. Q1 by 3. Q1 is what? Minus Q2 by 3. That would be 1 by 2 plus 1 by 9. That is 11. Q2 by 18 is equal to minus 4Q by 3. 3 is a 6 is a Q2 is minus 24Q by 11. Q1 will be minus plus 8Q by 11. That सब आ जाएगा. Check your answers. It's all about writing your equations properly and solving it. Any doubts on this? That's about shells. You can handle these 3 shells, then I think you can handle any type of shells. Any doubts on this? Clear? So the next part of this thing, right, is parallel plates, which we'll see in the next class. And mostly I think I should be able to wrap up in the next class. Time permits, we'll start off with the introduction of capacitors also. So please make sure to revise what we did today, right? Important thing. I know it can be a little confusing. It's not tough, but yeah, it's a little weird. Like we have not done anything like this without any equations and everything. We proved a lot of stuff. Okay, with that, we'll wrap up for the day, right? Do remember there's a test online till tomorrow, so make sure to give it. I'll see you guys again next Tuesday. We'll continue from here. So any doubts, anything else, please stay back and ask, or else you're free to leave. So take care, stay safe.